example 2.5. Here we're somebody has found for a particular system the molecular partition function, and it's given by z1 equals a t to the fourth. And what you're asked to do in this case is find the internal energy of the system from this molecular partition function for 1 mole of the substance that this was the partition function of. And remember, Z, just a good point to remember, the partition function for the system is the molecular partition function, Z1 to the nth divided by n factorial. And if you take the logarithm, natural log of both sides, then the natural log of z1 to the n is just n natural log z1, and minus the natural log of n factorial. I can use, don't really have to in this case, but I can use the Stirling approximation to approximate this n factorial. Remember, n is on the order of Avogadro's number. In fact, in this case, we're looking at 1 mole, so it is Avogadro's number of particles. The Stirling approximation is very good for that large number, and so we can approximate really this natural log of n factorial with n natural log n minus n, which gives us that natural log of z is n natural log z1 minus n natural log of n plus n. And if I've got the partition function, then I can use this relationship here that we derived in class in some detail to calculate the internal energy for this system. And if you remember, it's just Kb, Boltzmann's constant, t squared, times the partial derivative of t, really with respect to natural log of z. So up here in this brackets, I probably should have written natural log z to begin with, but the natural log of z is n natural log z1 minus n natural log n plus n. And these last two terms don't depend on temperature. In fact, they're constants for a given amount of substance there. So the partial derivatives will vanish, and so the only thing that's going to give me any substance to this is the partial derivative of the first term, and that's just the one that I wrote here. However, so first thing I can do is I can pull this in all the way outside, which I did, and then I have to take the partial with respect to t of the natural log of z1, but I'm given that z1 is a t to the fourth, so I have to take the natural log of the product of t to the fourth. And that one is pretty easy to do. It's the natural log of t to the fourth here, plus the natural log of a. And the natural log of t to the fourth is just 4 times the natural log of t. If I take the partial derivative of this whole thing in brackets, a is a constant, so the partial derivative with respect to t of a constant will vanish. And I can bring the 4 outside, and I'm down to just the partial derivative with respect to t of natural log t. And the derivative of the natural log is 1 over, of natural log of t is just 1 over t. And so I can rearrange this. Oh, I didn't talk about the front part, but we've done this a bunch of times anyway. I have this expression. I can multiply and divide by Avogadro's number. Na times Kb is just the ideal gas constant. And then N over Na is just the number of moles of the substance. So I carry that through. And so really I've got the internal energy of this particular system is 4 nRT, where n is the number of moles. And so for 1 mole of the substance, if you like, you can just put one mole in here. Or you can come here and compute uh, the divide both sides by n. So this would be the internal energy per mole is 4RT, and then you have to interpret this as the internal energy per mole, or for just 1 mole of the substance.